So our common applications that we look at, we have position, acceleration, and velocity. That's pretty common to look at, but we're going to finish out this section with a few other quick examples. In science, they study density, mass divided by volume in 3 dimensions, and in 2 dimensions you can do linear density, mass divided by length. So if you have something like a long rod or a piece of wire, if you ignore the thickness, you can talk about linear density, mass divided by length. And that could be uniform, but often the mass might change as you move along the object. So we talk about the linear density. The derivative gives us the linear density, the rate of change there in mass divided by length. So suppose the mass of a rod is given by a function x squared grams at x centimeters. Find the density at 3 centimeters. So this one's simple enough. Take the derivative and we get 2x by the power rule. And then plug in 3, we get 6 grams per centimeter, output over input there, 6 grams per centimeter. So as you move along the rod, it's changing at 6 grams per centimeter when you're at 3 centimeters. In biology, anytime we have a population that's changing, we could look at growth rates. Derivatives would give you the instantaneous rate of change in a population. We could model this and very precisely and come up with the formula for the function, but we're just going to approximate here on this example. The population of a city is doubling every 5 years. If its current population is 20,000, what would be its approximate population 2 years from now? So the derivative there, we can approximate the derivative at the current time to be 20,000 divided by 5. It's going to double, increase by 20,000 people over the next 5 years. So that's an average of 4,000 people per year. So we'll use that to estimate the derivative at the current time, which I'm calling x sub 0. And then we just apply that over a 2-year period. The population at 2 years from now would be the population it is now plus a rate of change times 2. So you wind up with an additional 8,000 people. In economics, there's a lot of things they study in economics and use derivatives for. A common one is your cost, how much money it costs to produce items, the revenue, how much you make from selling, and then your profit, which is revenue minus cost. Each of those, when you take the derivative in economics, they call it the marginal function. So you have the marginal cost, the marginal revenue, the marginal profit. We're going to look at marginal cost in an example here. So suppose that a company produces an item according to the cost function. Here we have C of Q, depends on the quantity Q. It's 10,000 plus 12Q plus 0.005Q squared. Find the marginal cost function, which is just going to be C prime, and then find at the particular value C prime of 750 and interpret the results. So just apply the power rule. You'll wind up with 12 plus 2 times 0.005 gives me 0.01 Q. Then we can plug in 750 to that and I wind up with 19.5, but those would be dollars per item. And the interpretation there, it's an instantaneous rate of change. So you can think about going from 750 to 751 at the time that you're at 750 items. To increase the quantity by 1 would cost about $19.50. So these were just a few quick examples, but as it says here, anytime you have a function relating two variables, if you look at the derivative, you're going to see the rate of change. How is your output changing as your input changes? So these can be extremely useful in the real world if you want to see how things change.